Hi, today we're going to look at, writing reactions and learning the 5 types of reactions that we will use in honors chemistry class. Before we jump into it, I wanted to talk about one thing we haven't talked about yet, which was the 7 elements that don't exist by themselves in nature. You can call them lots of things. Sometimes they're called the sneaky 7. Ooh, spooky. Sometimes they're called, I made up Stairway to 7, so thank you for that. I think that was a really good one. They're easy to remember, and they, like I said, exist in nature as pairs. You probably know some of them, like, for example, if I said oxygen to you, you'd be like, oh yeah, oxygen, that is O2. And there are 6 other elements that are like that: oxygen, nitrogen, fluorine, chlorine, bromine, oopsies, that should be a 2. Iodine, is that 7? What am I missing? Nitrogen. Nope, got it. Oh man, this is embarrassing. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Oh man, that was a tough one. That was embarrassing. So those 7 elements, when they're by themselves, they pair up. So of course you can have, like, NaCl and say, like, oh, Mr. Summers, there's only one Cl there. That's true. It's just that if you were saying something was by itself, like, let's say Na plus Cl, well, the Cl, it doesn't exist like that. It exists as a pair, and so it gets a 2 there, okay? That can be tricky as we move on to types of reactions, because when I say chlorine, you have to remember, oh yeah, chlorine's a sneaky 7. So on the periodic table, they're easy to find. I put periodic table right down here. Check it out. This is a good way to remember them. Start at element number 7 and make a number 7. Oh man, look at that. And then don't forget hydrogen. Okay, so this is like your 7 over here. Okay, it's not a grade 7, I get it, but it's something. We can at least go for that. So those 7 elements will pair up when they are alone. Again, alone only is the key. So now that you know that or been told that, let's talk about these types of reactions and how you can write reactions out. So the way that you want to rate reactions is that you have to first learn the 5 types. And so I have 5 types here. And if you're just writing in your notebook, you have lots to write. And if you're using this little template, you probably don't have much to write. So the general form of the first kind of reaction is called a synthesis reaction. So general forms here, I'm just like saying, I'm just putting some dummy variables in here. So in the general form of a synthesis reaction, you take 2 elements and you make them into a compound. So basically just take A plus B, and then you make them into one thing like that. So that's what it says here, where A is a compound, A is an element and B is an element, and then together they form a compound. That's called a synthesis reaction. And one that we just, actually as an example, talked about for that would be sodium chloride. So if you're going to make sodium and chlorine, again, chlorine's a sneaky 7, so it gets a 2 like that. If you're going to make them, let's do better arrows. Let's just hold ourselves to a higher standard. There we go. Not much better, but whatever. So, and you're going to put them together to make NaCl. Now, here's the trick, okay? Whenever you're going to put things together, like I did here, you have to crisscross them. And I know that you've been working very hard on crisscross, so you know how to crisscross. So synthesis is a kind of reaction where you have to crisscross. And that's important to remember. Whenever you put 2 elements together, they don't just smoosh together, you have to crisscross them. And I did that because I know that Na is +1, Cl is -1, so they just cancel out. Okay, but that's important. Now, Mr. Summers, you're like, Mr. Summers, they're not balanced. Yeah, you can balance these because you know how to do that now too, right? So I got 2 Cls, so I'm going to put 2 Cls there. That gives me 2 sodiums, so I put 2 sodiums there. So there's your correctly correctly balanced and written synthesis equation for making sodium chloride from salt and from chlorine. Okay, let's look at the next kind. Excuse me. Next kind is the exact opposite of the synthesis. It's called a decomposition reaction. In a decomposition reaction, you are just taking a compound and you break it into its pieces. So the general form is just flip it around, A, B, and then you break it into A and B. I like to put sneaky 7s as examples here. So like here's an example, potassium fluoride. Okay, break it apart. And you get potassium, and you also get fluorine, but guess what? Fluorine's a sneaky 7, so it gets a 2. Is potassium a sneaky 7? It is not, so it does not get a 2. So remember that. That's the fluorine can be 1 here when it's in a compound, but when it is alone, it gets a 2, pairs up, okay? Kind of like that friend of yours who is like always dating someone. Fluorine and the other sneaky 7 are always paired up with themselves. And if you don't know who that person is in your friend group who's always dating someone and never alone, it's you. Okay, so, balance it too. Let's balance by putting some 2s in there. a 2 here and a 2 there would work to balance this decomposition reaction. Again, it's the opposite of a synthesis reaction. And notice I don't need to crisscross here because I'm not putting two things together. I'm just taking a thing apart. So that's important. You do not need to crisscross there. Next one, excuse me, combustion is actually a little bit different. And you've seen a couple of combustion reactions. We've talked about them a little bit in class before. In a combustion reaction, you have something with C's and also H's and also O's. And I put X, Y, and Z there as the variables. You can have any number of them. And so it will have something like that. It might not have any O's, but that's okay. This is not a 2, it's a Z. But it always reacts in this way, always reacts with oxygen, always makes the same two things, carbon dioxide and water. Maybe you noticed this as we've been doing these problems, and we've done a fair amount of balance in combustion reactions, but now you can see that in a combustion reaction, these things are always the same. Always carbon dioxide, water on the product side, always reacting with oxygen on the reactant side. The only thing that changes is the fuel that you use. And so sometimes you have O's there, but not always. And it will always have at least C's and H's, okay? And the fuel could be anything. We've talked about, excuse me, lots of different fuels or starting materials for combustion reactions. So that is a typical combustion reaction. And these are the easiest ones, right? If I said something combusted, you'd be like, oh, combusted means it always reacts with oxygen and always produces carbon dioxide and water. So technically no crisscross here because it's always the same two things on the product side. An example might be like, let's say, pentane, C5H12 is pentane, not that you need to know that. And it's going to react with oxygen, and it's going to always make carbon dioxide and water. And the trickiest part about these is balancing them. So we've done some practice with these though too. So balance these ones in particular in alphabetical order. So carbons, 5 carbons, so 5 carbons there. And then hydrogens, there are 12 right here, so I put a 6, because 6 times 2 is 12. And then I add up all the oxygens on this side, which is 10 plus 6 is 16, so 8 times 2 is 16. So there's my correctly balanced combustion reaction. Now the last two are sort of related, and you're going to crisscross on both of them because you're going to put some things together. The first one is called a single replacement reaction. In a single replacement reaction, you have A and B, C, and so you have like an element and a compound, and basically the A kicks out one of the elements from the compound, so you get A, C, and B. Something like that. This is also sometimes known as Summer's Prom 1996, where someone is kicked out. I'll let you guess. Okay, so in this reaction, A kicks out B. Now B is all alone. Again, it strikes very close to home. And an example would be magnesium and hydrochloric acid or hydrogen chloride. Okay, in this problem, the metal, which is this one, replaces, well, I know technically hydrogen's not a metal, but the A replaces the first thing. The A replaces the B always in these problems. And so now you're going to get, you're going to put things together, right? So look, I'm going to put Mg and Cl together. So you're going to crisscross those, magnesium plus 2, chlorine minus 1. So you crisscross them and get that. And then hydrogen is by itself. And don't forget, hydrogen is never actually by itself. It always pairs up. It's a sneaky 7. So it gets a 2. It's one of the ones that's up here. So you'll need to remember that for a lot of these problems. And then we can balance it by putting I think we need 1, 2 right there to balance it out. So there's a single replacement reaction of magnesium replacing hydrogen in hydrogen chloride. This one also, as I mentioned, is going to need crisscross. So whenever you're putting things together, you have to crisscross them. You cannot just smoosh them together. Crisscross. Last one is called double replacement. And in double replacement, you're just, instead of having one element, they're just going to switch places. So we've got 2 compounds, A and B, and you also have C and D, and they're going to, basically the A and the C switch places. So you're going to get, in this order, very important, A, D, and also C, B. Excuse me. An example of a double replacement reaction like this would be maybe, I don't know, let's say cesium fluoride and strontium nitrate. Okay, and so it's helpful sometimes to label them, like the A is this one right here, this is the B, this is the C, and that's the D. And on the other side, A and D go together, and C and B go together in that order. You're putting 2 things together this time, you need to crisscross 2 times. when you do this. So cesium is going to be with nitrate. Cesium is +1, nitrate's -1. So they cancel out, CsNO3. Then strontium is with fluorine. Strontium is a +2 and fluorine's a -1. So SrF2 when you crisscross that. Again, I'm crisscrossing those whenever I'm putting things together. Mr. Summers, there's 2 fluorines on the right-hand side, but there's only 1 fluorine on the left-hand side. Yes, of course. So we balance it out to make sure everything works. You've got 2 fluorines on the right, so put 2 there. That gives you 2 cesiums, so put a 2 there. That gives you 2 nitrates, and guess what? We already have 2 nitrates on the other side, so we're set. This is a correctly balanced double replacement reaction where the 2 things switch places. Okay, I thought it'd be good also to try a couple as examples for you while you are taking notes today. You don't have to do all of these. I'm just going to work through a couple of them, and we'll just go through and see. So the big part is just kind of identifying first what it is. And so if we look at number 1, you have 2 elements together, right? An A by itself and a B by itself. So I'm sorry, I meant 2 elements like it's 2 individual elements reacting with each other. Okay, and that, if you look at that, you say, okay, well, what does this look like? An A plus a B, and if you scroll back up to the top here, you'll see A plus a B looks like a synthesis reaction. And we're going to put those 2 things together. Oh my gosh, I forgot my highlight. Oh my gosh, so bad at this. Highlight double replacement, because double replacement, of course, is a crisscross reaction. Oh, it gets pink. So back to this one. It's going to be just putting these 2 things together. Now, you can't just go like this, okay? You can't say AlO2. That's right. It's not right because you got to crisscross whenever you put things together. Very important. So, you've been very good at crisscross. Aluminum is +3. Oxygen is -2. So when you crisscross those, you get Al2O3. Okay, that's how you write the correct products. Okay, I'm going to write an S because this is a synthesis reaction, just showing you what it is. And after crisscross, then you balance it. So it's got like a lot of pieces to do. Everyone loves like having a lot of work to do. Let's see, 2 oxygens, 3 oxygens, so get them both to 6, put a 2 here, put a 3 there, and then 4 aluminums to balance it out. And of course, classic Mr. Summers, I've written so much there, but you really only need that. I classified the reaction as synthesis, I wrote the products, and then I balanced it out. I'll just try a couple more for practice, and you should try them too, okay, just to see how they're done. So pause it after I start one. Let's look at number 2, let's say. Okay, 2 looks complicated, but you have to remember here on number 2 that this is something with C's and H's, and this is oxygen. So it looks like sort of a backward single replacement, but in reality, what you're looking at is a combustion reaction, okay? And combustion reactions are your favorites. Remember prefixes from last unit? You're like, oh, yay, prefixes, I'm so happy. Combustions is like the best, too, because it's always the same 2 products. It's always carbon dioxide, and it's always water. No thinking about that, just write it out. That's what it always is. And then the challenge, as I mentioned before, is balancing them sometimes, although this one's pretty straightforward to balance. We're going to start with carbons, put a 3 there. Hydrogens, there's 8, so 4 times 2 is 8. And then add up all the oxygens. 3 times 2 is 6, plus 4 is 10, so 5 oxygens on that side. So there's your correctly balanced and written combustion reaction. Generally speaking, the ones that look more complicated are the ones that are going to be a double replacement or at least a single replacement reaction. So we'll try a couple of those too. You know what? We're just going to do them all. All of the types, not all of these things. So how about we look at, let's say, there's some challenging ones here. Number 9. Number 9, you're starting with a thing, A, B, okay? And there's nothing else. So these are easy to identify. This is a decomposition reaction. It doesn't have any pluses on the left-hand side. It's just take a thing and break it apart. So if I'm going to break apart ammonia, it doesn't matter that it says a 3 there. Or that it says a 1 there. I'm just going to break them into their individual pieces. And the individual pieces are both nitrogen and hydrogen. But the trick, of course, that's not hydrogen. The trick, of course, is that both of these are sneaky 7. Okay, so they can't just exist by themselves. They have to get 2s for this problem. And then you say, I'm Mr. Summers, it's not balanced. That's correct, right? So when they have the 2s there, that's why you have to work a little bit harder to find the balancing to make it work. So and balancing, let's see, hydrogens should go first, although it doesn't matter. You'll figure it out either way. You've got 2 hydrogens there, 3, so we're going to make them both 6 by putting a 2 there and a 3 there. And that 2 gives you 2 nitrogens, and guess what? We already have 2 nitrogens, so it's all balanced out. So let's see, we've done synthesis, combustion. This was decomposition here. And now we're going to try to find a single replacement one that's not going to hurt your feelings too hard. And I guess that would be number 7. Okay, you can identify single replacement because it's like, oh, a thing by itself and then a thing together, A plus B, C, there you go. And in a single replacement reaction, what happens is that A and C go together and B is now all alone, and you have to crisscross when you put A and C together. Take a second right now if you want to try it on your own, and then you can check with my answer. Okay, so cesium replaces hydrogen. Cesium is a +1, sulfate's a -2, so I'm going to put those two things together, cesium +1, sulfate -2. Crisscross them to get the correct formula, which is CS2SO4. And then hydrogen is all alone. Hydrogen's all alone, but hydrogen's a sneaky 7, so it actually gets a 2. It's never totally all alone. So there is your correctly written product, single replacement, and then you balance it out by simply putting a 2 over here. Easy to do. That was the wrong 2. Oh dear. Not great. Okay, there you go. Balance it out for my single replacement reaction, which leaves us for a double replacement reaction, and I think number 11 fits our bill there. Try it on your own if you want to, while I get all my pen clicks and things set up here. You can identify it. It looks more complicated, but here you go. There's your A, there's your B, this is C, this is D. On this side, A and D go together, and C and B go together. You can write it the other way. You can write, CB here and AD there. But you can't switch the order, so you can't write B, C. That's not the way that things work. So anyway, A and D go together, C and B go together. Let's put them together. So again, you're going to crisscross 2 times here because you're putting 2 different things together. So sodium is +1 and sulfite is -2. So when you crisscross them, you get Na2SO3. I know you guys are good at writing and crisscrossing. You've all done very well at it, so I'm not going to write the charges out for you, but I'll say them. And then aluminum is going to go with hydroxide. Aluminum is +3, and hydroxide is -1. So when you crisscross them, that is the formula that you get. And then, of course, the challenge for these ones usually is balancing. So there are the correctly listed products. And here, I'm going to say that this is double replacement reaction. And, Amanda, where do you want to start? I'll tell you. Aluminum is where we're going to start. So aluminum 1 here, so I'm going to put backwards. 1 there, 2 there, put a 2. That gives you 6 hydroxide, so put a 6 there. That's 6 sodium, so put a 3 there. 3 times 2 is 6. That gives you 3 sulfites, and guess what? You already have the 3 sulfites right there. So there's your correctly identified and written reaction for sodium hydroxide and aluminum sulfite. Okay, so there now you see kind of in action how you can do the 5 different types of reactions for this class. It's all about identifying them, and I think really helpful is just like mentally picturing, like at least mentally, but you can write them down if you want to, like what is going on for each of the pieces, and that comparing them to our list here, and then saying, okay, that's this kind of reaction, so that's what I should use. Anyway, this has been super fun. Always a pleasure to check in with you guys. Take care. Bye.